Hello, Priyankar.
Hello.
Yeah, can you just try sharing your screen first? Hello.
Yes.
Can you try sharing your screen once?
Uh, okay. Okay.
I will zoom in a bit.
Okay. Hello. Is the screen visible?
Yeah, the screen is visible. Uh, then am I audible? I'm just asking. Hello. Can okay, okay, thanks.
Uh,
Priyankar, can you hear me clearly,
yes.
or is my sound breaking? Yeah, maybe we'll wait for 1 or 2 minutes, then we'll start. Is that okay for you?
Uh,
Ah, I see. Uh,
yes. Now.
can others hear me?
Okay.
Yeah,
Okay.
we
Okay.
can hear you.
Okay. Priyanka, can you just once more check your internet, please? Maybe there's your connection issue or something, because others can hear me.
Okay.
Hello everyone. So welcome to the last and final session of today. So today we have Priyankar Biswas. He's from ISA Bangalore. He's the first year over here. So he'll be talking about introduction to partition identities. So over to you, Priyankar.
Hello everyone, I am Priyankar Biswas. Today I'm going to talk about partition
I'm not
identities.
able to hear you.
Partition is a partition of a natural number. This is the way you can a positive integer as a sum of other positive integers.
Can others hear him?
The sound is a bit wobbly.
Oh,
Can you try moving into a better places?
hello everyone. Am I audible now?
Yeah, you are.
Okay. So today we'll talk about partition identities. Partition of a positive integer is this is a way of writing a positive integer as a sum of other positive integers, where this order is doesn't matter. And the partition function is a function from natural numbers to natural numbers, which gives number of ways you can partition a positive integer. Here you can see that in the example, we can write 4 as 1 plus 1 plus 1 plus 1, 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 4. And these are the only possible ways we can write 4 as, mm, I mean, we can partition 4. So partition of 4 is 5. Uh, but in today's topic, we will discuss about partitions given different type of conditions, like partition given a partition of an integer given odd number of distinct parts, or like this. So before that, we need to before going into the
I'm sorry
proofs
to
and
interrupt.
the,
Can you just zoom in a bit
yes,
because showing half only the half the page is content. Yeah.
okay, okay.
Little bit more. Yeah. Better.
Is it okay?
Yes. Yeah.
Fine. Is it okay now?
Yeah. Much better.
Okay. So before going into the proofs and the deep of the theorems, we need to know some basic things to understand the proofs. We need some basic of combinatorics and analysis to get through some of the proofs, except that we need to know about Ferrier graphs and generating functions. Well, a Ferrier graph is a number of way. Ferrier graph is a way of representing a partition. Uh, Here you can see that we are giving a partition of 12, 4 plus 4 plus 2 plus 1 plus 1. So the Ferrier graph, we represent it in this way as first part. First of all, we have to make it in decreasing, non-increasing order. Then uh, then arrange it in strings of dots or strings of boxes. Like here, this is four. There are dots. Here are 4 dots. Then 2, and then 1 and 1, and you can also represent it as in box forms. So is Ferrier graph understood to all of us?
Yes, sir.
Uh, Okay, so next we will go to generating functions. Well, generating functions is suppose f is mm, a function from natural union set containing 0 to real, and the generating function of this function is the formal power series, which is sum from n equals to 0 to infinity f of n q power n. And here this may or may not converge, as this is a formal power series. But when this thing converge, uh, a study becomes really interesting. We'll see about this later. And here's
Was
an
there a
example of
generating
generating.
function for this also, like for partition? I heard that there was a
Uh,
generating function for partition.
yes, yes, there is generating function of partitions. Well, you can write generating function. Well, partition functions have generating function this 1 by 1 minus q power n, and
Yes,
product
yes.
of n equals to 1 to infinity. I think this is what you are talking about.
That actually, yes, that actually comes from an infinite product, like product of infinite product, like yeah, product of infinite sums.
Product
Yeah,
of infinite sums.
like
Yeah, yeah, yeah. We'll talk about this. We'll talk about different type of generating functions in this topic. So now we'll go to the proof strategies. uh, we have basically two type of proof strategies in this case. One is to find a bijection from set of all types of partitions from one to another, and one is to show the generating functions as same. Well, the second way is this is used in many type of complicated cases where you cannot find an easy bijection from one set to another. Now we'll give some easy examples. Here, the first example is partition of n given even number of odd parts equals to partition of n given odd number of even parts. Here, this is an easy example. You can see if you draw the Ferrari graphs of any type of partition in partition of n, so even number of odd parts. If you flip the Ferrari graph, this would be partition in odd number of even parts. Can anyone give me an example of uh, such partition of even number of odd parts of any integer? Hello?
Yeah.
Uh, Yeah, can anyone give me an example so that I can explain through graphs?
3 plus 3 plus 2 maybe.
Okay. So this is paragraph would be like this, and if we flip the paragraph, then we will get basically the same partition. But
Can you please show from the first, because now only I joined.
what?
Uh, Please, can you show from the first slide, because I joined now.
Oh, okay. So I'll I will say this rapidly. With partition of positive integer, partition of a positive integer is number of is a way of writing is as sum of other positive integers, where the order doesn't matter, and partition function is a function from natural to natural, which gives number of ways you can partition a positive integer. Here you can say, right, partition of 3, you can write 3 as 3 and 2 plus 1 and 1 plus 1 plus 1, so partition of 3 is 3, like this. And then we have talked about some preliminaries to understand this, understand the proof of some partition identities. The partition identities mainly deal with partition given any condition, like partition given all all parts are odd, or like partition given all parts are distinct, like this. So we will deal with this type of things and relation between them. We will talk about the proofs also. Before that, we need some basics to know, like Ferrar graphs. Ferrar graph of a partition is a way of representing in partition in a graphical way. Like here, mm, can you tell me partition of a positive integer? I'll draw the Ferrar graph. Hello.
Sir, 3 plus 2 plus 1.
So the Ferrar graph is first you have to write the biggest part in as a string of dots or boxes, and this two you let the in this next arrow in the next row, and then one. This is the Ferrar graph of this partition. So, is it okay? Mm. Is this part okay?
Yes, sir.
Generating functions. Well, generating function is a function from natural set. Say you have a function from natural union set containing 0 to real, or this can also be complex. The range. Then the generating function is sum over n equals to 0 to infinity f of n q power n. This is a formal power series. This does not need to be need to converge. But if this series converge, then this study is really interesting. Here is one example. Like in choose n, the generating function of this is 1 plus q power n, and it also say that the generating function of this sequence only one, like this 1 1 1, this sequence generating function of this is just 1 plus q square, this which is nothing but 1 by 1 minus q in the region where q is say -1 to +1 open. The generating function okay.
Yes.
So now we'll head towards the proof strategies. There are basically two types of proof strategies. One is to find a bijection from set of all types of partitions. Here we are trying to here partition identities. Basically, we try to prove equality between some type of partition from some type of partition of a positive integer and another type of partition or positive integer given some specific conditions. Like partition of, I'm just giving one example, partition of n given all parts are distinct equals to partition of n given all parts are odd, like this type of thing. So basically here we make bijection from set of all types of partitions from this to this, and next we can also find a and next we can also show that the generating function of these two are same. This is also a way of showing that this is also one way of showing the equality between these two. So here we have started with some easy examples, like partition of n given even number of odd parts equals to partition of n given odd number of even parts. This say we have here we'll flip the Ferrar graphs, and this should give an invertible transformation from one type of partition from this side to this side. Say we have one type of partition, like partition of 7 in this way, even number of odd parts. Oh no, we cannot do for 7. Say we have 8 and we are partitioning it in even number of odd parts. So it is 3 plus 5 plus 3. So here we'll get the Ferrari graph in like this. And if you flip the Ferrari graph, this would be like this. So here you can see we have get one partition from this side, partition of odd number of even parts. So, and for this second second identity, this also you can be this also you can prove like this. Partition of n less than or equals to m parts equal to partition of n given all parts less than or equal to m. Here you say we're talking about partition of n given less than or equal to say 4. So we are say and we have will show that this is equal to partition of n given all parts less than or equal to 4, less than or equals to 4 parts. So here let partition of 7 in this way less than or equals to 4 parts. So say the partition is 5 plus so 4 plus 2 plus 1. So the Ferrari graph is like this, and if you flip the Ferrari graph, the partition will be this is less than equal to and here the all parts are less than equal to 4. Is the second one clear? Hello.
Let's say if the number was 17, how would that work?
17.
Yeah, like if the number is 7, then even number of odd parts is not possible, right?
Oh yeah. This one is not correct. I think. I think the first one is not correct. Okay, so for the second one, the second one is okay. Hello.
Yeah, okay.
Yeah. So next, the partition of n given odd distinct parts equal to partition of n given self-conjugate partitions. So the self-conjugate partition is like this. If you place a mirror diagonally, then this would be this side. So if you if you flip the graph, then the partition is still same. So here we will give take the transformation like this. If you are given odd number of if you are given odd distinct parts, like here we are given 7 plus 3 plus 1. Here we will break it like here we will make it like this one. There are 4 points and there are here also 4 points in the row and 4 points in the column, and we'll now cover this like this and then go like this. I mean, can you understand that, what is the transformation is like happening? Hello.
Yeah, we get it.
Okay.
Yeah.
So next, partition of n given odd parts equal to partition of n given distinct parts. Here will here the transformation is like if you are given say partition like 1 plus 3 plus 3 plus 3 plus 5, then this is a this is a partition of the form n given odd parts. Now we will join two parts if they are same. Like here we have joined 3 and 3 and we have got 6, and this process will go on until all of the parts are distinct. Like if we have got 3 plus if we have got 4 threes, then first we will join 2 threes, we will get 6 and 6, and we still haven't got all parts distinct, so we'll then also add 6 plus 6 to get 12. And the reverse transformation is if any part is even, then we have to break it in equal parts, two equal parts, and if it is still not odd, then break those parts also. In this way the transformation goes on. So now this is an invertible transformation from set of all type of partitions from odd parts to set of all type of partition of distinct parts. So this shows the equality. Now in the next way you can show this using the generating functions. Generating function of partition of n given odd parts. This is G1, which is n equals to product of n equals to 1 to infinity 1 by 1 minus q to the power 2n minus 1. Is everyone okay with this, or should I explain this a bit? Hello.
Yes, sir, it's clear.
Okay, so like this product of,
Please explain it.
you can write this product like this. And say if we want the coefficient of capital N, so we can get this the number of ways you can represent N as sum of odd parts may not be distinct. Like say we have you want the coefficient of q power 8. So here we want the coefficient of q power 8 from 1 plus q plus q square plus 1 plus q cube 3 into 2 plus from this. So we'll get this number of ways. You can write 8 as this sum of this exponents, right? So you can write 8 as say 2 plus 6, or you can write 5 plus 3. So then this will be counted, and these are the sum of the and these things are coefficients or sum of number of ways you can represent it as a sum of the coefficients of the powers of this, which are the some multiple times odd. Is this okay?
Yes, sir.
Yes, sir.
So, and similar way you can get coefficient of the another part, which is the coefficient of a partition of n given distinct parts. Sorry, the generating function of this would be n equals to 1 to infinity 1 plus q power n, as the coefficient of say capital N. This would be the number of ways we can represent it as a sum of the coefficients of this as sum of the coefficients of uh, q power n. So let we want to find the coefficient of 8. So this would be number of ways you can we want the coefficient of q power 8, and here we have got this expression. So you can see that we can represent it the coefficient of q power 8 is number of ways you can represent 8 as sum of a sum of these coefficients 1, 2, and so on. And here all the parts should be distinct. So now the generating function, so the coefficient will be partition of n given distinct parts. Is it okay?
Yes, sir.
So we will just have to show G1Q equals to G2Q, and that is equivalent to show that is equivalent to show this n equals to 1 to infinity 1 plus q power n into 1 minus q power 2n minus 1. This would be equal to 1, and you can show this in this way. This product 1 minus q 1 plus q whole power n, you can break it in this form, because 2n minus 1 into 2 power k, where n varies from 1 to infinity and k varies from 0 to infinity, this cover all type of natural numbers. So now we can write this as 1 minus q 2n minus 1 and k equals to 0 to infinity, this product, which is nothing but this limit k tends to say this up to some finite term positive k. So, say you are writing this as a finite product. Say here not infinity, we will get capital K and limit capital K tends to 0. So the product will be so the expression will be limit capital K tends to 0 1 minus q power 2n minus 1 2 power capital K plus 1, and this would be 1, and over this is product over all natural, so the final result is 1. You can make this rigorous, more rigorous using some real analysis, but for now is this proof okay? Hello?
See some thumbs up. So you can go ahead.
Can you say again?
It's that
I can see some thumbs up. So you can go ahead.
Okay. So next we'll talk about Euler's pentagonal number theorem. So Euler's pentagonal number theorem is partition of n given even number of distinct parts minus partition of n given odd number of distinct parts. This is equals to En, where En is minus 1 power j, where n is either of the form j into 3j plus 1 by 2, or either this is j into 3j minus 1 by 2. So here in this proof, we'll make a bijection from not a bijection, we'll make a transformation from partition from n given even number of distinct parts from odd number of distinct part. Well, the transformation is given any Ferrar graph of type of any type. Say if say P1 is the set of all types of partitions of this form and P2 is of this form. So say we are given any partition of the type Pi. So now the now consider the transformation as if the rightmost diagonal, see the rightmost diagonal, if it is smaller than the smallest row, then cut it and shift it here, and if it is not smaller, if they are equal or this is smaller, then cut the smallest row and put it in this diagonal form. Say if we have here 2, so we'll take it from here to here and make it a diagonal length 2. Is the transformation fine? Or should I give an example?
Give an example.
Okay, so tell me any type of partition.
3 plus 2 plus 1.
So this is okay. So here you can see that the rightmost diagonal is this, and the smallest row is this. So the smallest, so here the smallest row, this is smaller than this diagonal. So now cut this and place this here. So you'll get a transformation. So you'll get a new paragraph. This and this. Okay. You can give if any complicated, if you make it complicated more. We want some more examples. Hello.
Suppose 7 plus 6 plus 4 plus 2.
Okay, so here the rightmost diagonal is this and this of length 2, and this is length 2. So the rightmost diagonal is not smaller than this. So again, shift it from here to here. The new transformation would be, and the new transformation would be like this. Okay.
Yeah, it's clear now.
So you can see, you can figure it out yourself why this transformation is an invertible transformation. Well, this is invertible, leaving only 2 cases. Well, if you get a paragraph like these 2 types, you will not get a partition from one type from another, or you will not get a valid partition at all. Say here we have a J cross J box. I mean, this box is a box of dots or box of boxes. This is a paragraph, and here is a triangle. And if you do now, if you do the transformation, here you can see we have here J many points, and here J plus 1. So we have to move this one from this, but if we move from this, the size of this would be of length J, and this is also of length J. Okay, so this is also J and this is also J. So here the parts are not distinct. So we are not getting a partner, a valid partition of the types which we want. Is it okay?
Yes, sir.
And for the next case, if you in this case here it is J minus 1, so we'll here get J points and here J points. So we'll move from we'll move this row from here to here, and if we move the row, you'll get that will J plus 1. So here we will get J many and then 1 point here. So this is also not a, I mean, you cannot make this type of transformation, because if you make this, if you make the transformation, then you will get something like this, but this is not valid. I mean, the size of I mean, this and this must of this same size, or this must be less than or equals to this after cutting this out. Here the picture is wrong. You will you cannot actually make a partition. Like if you cut from here to and if you cut j points from here, and if you try to fix it here, you will get that here are here are j many points, and here you will get j plus 1. So you cannot fix this. This would make something like this, which is not valid, not a fair graph at all. Is it okay?
Yes, sir.
So only in first case you will get that that number of points here is j square plus j into j plus 1 by 2, which is j into 3j plus 1 by 2, and next case is j into 3j minus 1 by 2. So in both of these cases will and these are the only cases where we will not get a partition from one type to another. Test different type of cases and check why these are the only two cases, and you can and this is easy that this set of all types of j into 3j plus 1 by 2 and j into 3j minus 1 by 2, but j belongs to natural number. This set does not have any I mean, this set does not have any intersection. There should be k. I have written wrong. So only in this type of cases you will get one partition extra in either of the types, P1 or P2. If j is even, so we will get one even number of distinct parts extra, and if j is odd, we will get odd number of distinct parts extra. So our partition identity is true. And the next way is to show use generating functions. Here generating function of the partition of n given even number of distinct parts minus partition of n given odd number of distinct parts is this n equals to 1 to infinity 1 minus q power n, this product. Because if you say like how many ways you can get the coefficient of q to the power capital N, in this function we will get the coefficient of q to the power capital N as number of ways you can represent n as a sum of positive integers, say n1 to nm. In this case you will get the coefficient of q power capital N, where all of the ni's are distinct, and if m is even, we will get here +1, and if n is odd, we will get here -1. So finally you will get the coefficient to be this. Is this okay? Is this okay? Why this coefficient of q power capital N should be this?
It should be a thumbs up. So,
Is this part okay?
Oh yeah, it is.
Okay, and the next, and the generating function of En, this is easy. -1 power j, q power j into 3j minus 1 by 2, and q power j into 3j plus 1 by 2, which if you write, this should be j equals to minus infinity plus infinity -1 power j, q power j into 3j minus 1 by 2, or you can replace it in 3j plus 1 by 2. So only now we have to show that these two generating functions are same. And to show this, we need something called Jacobi's triple product identity. And this comes directly from the identity. The Jacobi's triple product identity, before going, I'll state this first. This is Jacobi's triple product identity. I'll give the proof, but do you understand what this is stating? Hello. Hello, is the identity?
Maybe you can go ahead. You're doing it.
Okay, okay. So before going
Maybe
into
you don't need to pause every time.
okay, okay.
Yeah.
So before going into that, we'll need something to know about Dufresne square and Frobenius symbol. Well, Dufresne square is like I will explain to example. Here the partition of 12 is given as 4 plus 4 plus 2 plus 1 plus 1, and the largest possible left and uppermost box, this is this orange box, and this box is called Dufresne square. And the Frobenius symbol, this is a matrix representation of a partition where if you say we're given a if you say we're given a partition, first find what is the size of the Dufresne square. Say here it is 2 by 2. So find its size. Then the consider this matrix where the first where the I comma 1 comma jth entry. This is number of boxes on the right of the diagonal of Dufresne square of the jth row, and 2 comma jth element is number of boxes on the bottom of the diagonal of jth row. Suppose this partition of 23. So this is the diagonal, and this box is the Dufresne square, and count the number of boxes which is on the left on the of the first row of this diagonal. This is 1 plus 1 1 1 1 1 1 1. This is 7, and this is 6, and this is 1. This is 4 and 2. So the first element, the first 1 comma 1 entry, this is be 7. Then this is 6, which is this, and then 1, and then this is 4, 2, and 0. Is this part okay?
Yes.
So now we'll go into the proof. Well, that I am not going to talk about why these terms converge in this set, because this needs some pretty bit complex analysis, which I will not talk about now. In particularly this type of case, you can have a if you fix Q, you can have an expression of like this sum of, like you can in this particularly this case, if you fix Q, you can have expression AQ z power n equals to minus infinity to plus infinity. You can express this product as this sum. This type of sum is called Lorentz series expansion. In many type of case in complex analysis, you cannot find a Taylor series expansion around some point, but you can find a Lorentz series expansion around some point. Here in this case, you can find Lorentz series expansion around 0, and existence of this needs pretty bit of complex analysis, which I am not going into that. Suppose that you can have a Lorentz series expansion. Now we'll find what is the Lorentz series expansion. Uh, we put say the Lorentz series expansion of this expression 1 plus zq to the power n into 1 plus z inverse q to the power n minus 1. This part, this is say g of z. Now g of z, suppose this is this Lorentz series expansion we have got here. So put zq in place of z, you will get that this would be this will start from 2 to infinity, and this would from minus 1 to infinity. So if we manipulate something like this, 1 by z 1 plus zq, this is 1 plus z inverse q inverse, this is just this. As you can see that if we multiply this and divide by this, this is just g of z. So now we have got g of z equals to zq into g of zq. Now compare the coefficient of z power n plus 1 on both sides. You will get q power n plus 1 a n q equals to a n of q. And by solving recursion, you will get that coefficient of a n is q power n into n plus 1 by 2, a0q. And similarly, for negative integers, you can find it in recursive way that the coefficient is same. So we'll get the the g of z is a0q into n equals to minus infinity plus infinity z power n q power n into n plus 1 by 2. Now we have to find a0q. Well, a0q in this expression, sorry, in this expression, a0q is the a0q is the coefficient of, not the coefficient, a0q is this term. Well, if you sorry, this one here, if you get the coefficient of z to be 0 in this expression, if you get the coefficient z to be 0, then you have to get equal number of parts, like 1 plus z q to the power n1, 1 plus z q to the power n2, like this, and 1 plus z inverse q to the power n1 prime minus 1, n2 prime minus 1, like this. You have to get equal number of parts like this and equal number of parts like this. So the coefficient, the coefficient a0q will get this q to the power sum over s equals to 0 to infinity q power a1 plus a2 plus dot dot capital as b1 plus dot dot bs, where these parts come from the coefficient come from the part this, and bi's part comes from the coefficient of this. So this would so ai's would be ai's greater than equals to 1 and all distinct, and bi's would be greater than equals to 0 and all distinct. So and if we take out 1 from each of these parts, we'll get q power s and q power a1 plus up to dot as plus b1 plus up to dot bs. And finally, you will understand that the sum over this is just nothing but the number of ways, is nothing but the partition generating function of the partition function, because here whenever you get coefficient, whenever you will get q power capital N, you will get in this way, that number of ways you can represent n as a sum of s plus sum over ai's and bi's, where ai's are in where a is the largest, and then in decreasing order bs is the largest, and in decreasing order. And this is the, if you represent it in this form, in Frobenius symbol, we have a bijection from this. We have a bijection from a1 as to a product n, from bs to a product b, and this matrix from the partition of n. So if you get n, coefficient of q power n, you can get it number of ways, as you can represent it is this form. And if arrange it somehow like this. This is as many okay, okay, dots. There are as many boxes here, and this is as minus 1. This is now go on like this and complete as many boxes, as many dots here, and now bs from here to here, bs minus from here to here, and go on like this. This would give a paragraph. This is nothing but the construction of the what we did in the Frobenius symbol. So the coefficient of q power n is partition of n. Is this okay? Why this is true?
Yes, sir. Understood.
So we'll get a0q to be n equals to 1 to infinity 1 by 1 minus q power n, and now we have proved our result. And if we put the q cube in place of q and minus q inverse in place of z, you will get exactly the you will get like this: product of n equals to 1 to infinity 1 minus q to the power 3n, 1 minus q to the power 3n minus 1, 1 minus q to the power 3n minus 2, and this side you will get minus 1 to the power n, q to the power n into 3n minus 1 by 2. So now this is what we wanted to show for Euler's pentagonal number theorem. Well, can anyone guess why this thing is actually called Euler's pentagonal number theorem? Hello?
Yeah, there seems to be no response, but you can say it yourself.
Oh, okay, okay. So this is try to find out what is the number of well, there is this thing called polygonal number. Like in triangular number is like this. Consider this construction. The number of sorry, the number of total dots here in this case. If there are n many and there are n many, so you know that it should be n into n plus 1 by 2. Like this is what is total number of dots in this type of configuration is a triangular number. Total number of this is nothing but a lattice structure, and in square case you will get in square lattice total number of boxes. This is n square, and in type of pentagonal number you can also find you can try to construct a pentagonal lattice and then find total number of boxes in here. You will get that this is n into n minus 1 by 2. So that's why this is called the Euler's pentagonal number theorem. And now we'll come to really new thing, which is Gaussian polynomials. Here the Gaussian polynomial is defined in this way. Say this in capital N plus m choose m is of q is partition of n given number less than equals to m parts, each less than equals to capital N q power n, and this is some kind of function where if you put q to be 1, then you will get the binomial n plus m choose n, right? Because the Ferrari partition of n given less than equals to m parts, each less than equals to capital N. This is now consider this lattice. If you put n to be 1, then we will get the sum over n greater than equals to 0 partition of n given less than equals to m parts, each less than equals to capital N, which is nothing but the number of possible Fourier graphs in this way, that here are n parts, here is m, and the Fourier graph is like, say, like this. So each Fourier graph here represents a unique path from this point to this point. And the sum of all unique parts from this point to this point, this is capital N plus M, choose M. So that's why if you put Q equals to 1, this would not just be N plus M choose M. Now, a Gaussian polynomial, some similar types of properties like binomial coefficients. Here, n plus m choose m is n plus m choose n. This is because you can write. This is because you can write n choose less than equals to m parts, each less than equals to capital N. This is equals to less than equals to n parts, each less than equals to small n. This is just the flipping of Fourier graphs case. So that's why you get this first equality, and this is the second one. This comes from if you write partition of if you write n plus m choose m in this this is the definition, and break all types of partitions of n given less than equals to m parts, each less than equals to capital N, like this. Here the first row is complete and the first row is not complete. So if we get the the first column is complete and is where the first column is not complete. So complete means there these partitions are at least one. The size of the list size of these ones are at least one. And here we will get the parts strictly less than m, and here the parts are exactly equal to m. So for this case, you will get partition of n minus m less than equals to there are n minus m as this covers the m1 m many parts. You have to cover the rest of n minus m if n is greater than equals to m. So n minus m less than equals to m parts, each less than equals to capital N minus 1. And for this one, yeah, there are less than equals to m minus 1 parts, each less than equals to capital N. So you can break the sum like this. And finally, you will get this is partition of n given less than equals to m minus 1 parts, each less than equals to capital N q power n. And this is you can take out q power m, and this is q power n minus m. Partition of n minus m less than equals to m parts, is less than equals to capital N, n greater than equals to m. So this one by definition is n capital N plus m minus 1 choose m minus 1. This one also by definition. So if you use this and induction, you will get that. You will get this identity. Here and there are also some similar results with binomial coefficients, and I have I don't have much time to say about this, so I'll go this rapidly. You can check these things in the notes which I have sent you. So you know some results in binomial cases like -1 to the power j in choose j equals to 0 to n. This is 0, and for like this type of results where if you put q equals to 1, you will get the results of binomial theorems. So you can try this by yourselves. This is nothing but mainly using the first two of the formulas, this one and this one, and induction. And next we'll talk about the limiting cases of Gaussian polynomials. Limit, if you take the limit of capital N tends to infinity of capital N choose M, this is, as you can see, 1 minus u part, and here we are considering that q is mod of q is less than 1. So in this case, capital N choose if capital N tends to infinity, this part will become equal to 1, and this is 1 minus q into product 1 minus q power m. Here, this is a way of representing this type of products. This is a q Pochhammer symbol. Well, if this thing actually means this product 1 minus a 1 minus a q up to dot 1 minus a q power m minus 1. And this thing just 1 minus a 1 minus a q this goes on infinity. So for next one, Rn plus m1 and Sn plus m2, capital N tends to infinity. This is here you can see the on the numerator r minus s, this is greater than 1. Yes, this is greater than equal to 1. So this part will go to 1, and this would go to q comma q infinity, which is nothing but the genetic function of partition functions. Now we'll talk about the Roger-Ramanujan identities. I will talk about the first one, and then the second one is not actually, I don't know if it has any actual representation in partition forms, but it is expression in can you tell again? I cannot hear you properly. Hello. Can you write?
He's asking if you can skim through the remaining parts as the time is almost
Okay.
up.
Okay. So here I'll tell about only the sketch of the proof. You can get it in details in the.
Maybe you can just skip the proof and just go ahead with the theorem statement.
Okay. That's finally the statement is like these two identities of the. These are two functions where the mod q is less than 1. Is the disk centered at origin of radius 1 open disk. In this region, this identity is true. These identities are called Roger-Ramanujan identities. The second one has a particular interpretation in forms of partitions, which is nothing but partition of n given n given 2 distinct parts equals to partition of n given plus or minus 1 parts in plus or minus 1 mod 5. 2 distinct parts are here in distinct parts. The separation between two parts is at least 1, and in 2 distinct parts is at least 2. You can get any general m distinct parts also. So the second one has a particular interpretation like this. So basically, in the proof sketches, you have to find the partition functions of both sides, and then you have to find two functions, one of which the limiting case is the generating function of this, and the other one is generating function of this. So basically, you have to define all of these functions, and this Sn and sigma, and these two are actually equal. You can see the proof in the notes, and then if you take limit of n on the both sides, then this yields to the generating function of this part, and the sigma and on this part. This is the proof sketch. You can get it in details in the notes. So, and finally, I'll give some of interesting problems. Like you can see that the generating function of this thing, which is a partition of n given even number of distinct parts minus partition of n given odd number of distinct parts. The generating function of this is the inverse of the generating function of partition function. You try to find some recursive formula partition function using this, and then try to find try to prove these two identities where these conditions hold. Here you can use generating functions and try to find partition of try to find a generating function of self-conjugate partitions, and then try to prove this theorem. So this is over. If anyone have any question, you can ask.
What is
Thank you, Priyankar, for
self-conjugate
your wonderful talk.
partitions?
Yeah, someone has question. You can
What
go
is
ahead.
self-conjugate partitions, like the third one?
Oh, the self-conjugate partition is like the Ferrier graph is symmetric.
Oh, okay.
Like, okay. Any more questions?
Would you recommend a few references regarding?
Oh, sure. These are the two references for integer partitions by Georgie Andrews and Kimo Erickson. This is a good book for starting partitions, and if you want more rigor in these things, you need some basic complex analysis. You can read complex analysis from this book to find the rigor in the proofs.
Okay, thank you.
Are there any more questions? Okay, then let's thank Priyankar once more. That's it. I think Priyankar, you can send me the slides. I'll share with them, and I can check out those proofs that you did.
Okay.
Thanks.